Hi everyone, welcome back, and you're watching the seventh lecture of E635 Applied Linear Algebra. This happens to be the second module. Okay, so we were talking about linear maps, right? And we looked at two very interesting properties of linear maps, namely uh, when a linear map is one-to-one and when a linear map is onto. So let me remind you what this one-to-oneness and onto-ness uh, mean. So our premise remains the same. Phi is a linear map from vector space V to vector space W. Both of them are vector spaces over the same field of scalars. Yeah, phi is a linear map. So we say phi is one-to-one if phi is one-to-one if phi V1, okay, let me write it this way. If V1 not equal to V2 implies phi V1 not equal to phi V2. Then it's one-to-one. Phi is onto if for all W in capital W, this vector space, there exists V, probably more than one, but at least one V, such that phi V is equal to W. Then it's said to be onto. And then we have found out that phi, these two are very important results. Phi is one-to-one if and only if kernel phi is the trivial zero subspace only. Similarly, phi is onto if and only if image of phi is all of W. In general, it's a subspace, yeah, but for phi to be onto, it's necessary and sufficient that the image phi should be all of W. We looked at two consequences also of these two observations, namely when we are looking at a matrix A, which is an M cross N matrix, yeah, and it defines the map, defines the linear map A is a map from Fn to Fm. X is a vector that gets mapped to A times X. Then this linear map, this map is one-to-one if and only if A is full column rank, and this map is onto if and only if A is full row rank. Let us see quickly why should this be true. So this map A is one-to-one if and only if, as we have seen, kernel of A is equal to the zero space, right? But this tells us that from rank nullity theorem, dimension of, let me write it this way, from rank nullity theorem, dimension of kernel of A plus rank of A must be equal to dimension of the domain space, which is Fn. In this case, so kernel A being 0, this is if and only if rank of A is equal to dimension of f to the power n, which is n in this case, yeah, which then means that A is, so column rank of A is equal to n, which is equal to number of columns in A, which is the condition we name as A being full column rank. Okay, so kernel equal to 0 if and only if A is full column rank. That means the columns are linearly independent, which is kind of understandable because kernel A equal to 0 means, you see, whenever there is a vector, there is a non-trivial, non-zero vector in the kernel of A, that means that non-zero vector multiplying A gives us 0, the zero vector, which means because AX is linear combination of the columns of A given by X, the entries in X. If there is a non-trivial vector X such that AX is equal to 0, that means there is this non-trivial linear combination corresponding to the entries in X, linear combination of the columns of A, which goes to 0. Yeah, that means the columns are not linearly independent. So having non-zero vectors in the kernel is equivalent to having dependence in the columns. Likewise, kernel being 0 means the columns are linearly independent, which is equivalent to saying that the matrix A has full column rank. Okay. Similarly, this is one part. Similarly, A is on to if and only if image of A is equal to whole of W. This implies, this is if and only if column rank of A, which is equal to dimension of image of A, that must be equal to dimension of W, because image of A is all of W, but here this is dimension of F to the M, that is what W is. This is equal to M, but we know that row rank is equal to column rank, so this implies row rank of A is equal to M, but M is the number of rows. This is the number of rows in A, which means, this is the condition we call A being full row rank. So thus we get these two important facts that, where is it? Yeah, two important facts, this one and this one. Yeah, understandable? So 1 to 1, if and only if full row or full column rank, on to if and only if full row rank. Okay, so think about this. Now we are going to look at a situation. Oh, by the way, before I forget, we've already seen that one-to-one maps are also called monomorphisms or monic linear maps. It turns out that there is one more name for such maps, namely these maps are also called injective. I don't know, mathematicians, why do they give so many different names to the same thing? I don't know, don't ask me, but that's what it is. That's how it is. So these are same things, one-to-one monic monomorphism. Yeah, now comes the fourth name. It's also called injective. Similarly, likewise, on to epic, epimorphism, surjective. Some people also call it surjective. Okay. Now, when a map is both, when phi is both one-to-one and onto, then phi is called an isomorphism. Before we come to isomorphism, we'll say let us use this name, which is kind of similar to injective and surjective. It's called bijective. Okay. An immediate consequence of bijective maps is the following. So listen carefully. When phi is bijective, there exists a phi inverse, which is going to be a map from W to V such that phi inverse phi equal to identity on V, and phi inverse is identity on W. Yeah, by this I mean composition. Yeah, composition of two maps. Now, why is that so? Listen carefully. When I have bijection, first thing it's one-to-one. So that means different V's will go to different W's, right? That's one-to-one. Onto ensures that for everything in W, yeah, for every small w in capital W, there would be something here, something in capital V, say small v, such that phi V is equal to W. Okay? But one-to-one, now onto means for everything in W, I have something in V. But moreover, if I also insist on phi being one-to-one, then this would mean that this W that I have, small w, in capital W, I pick an arbitrary small w in capital W, then the corresponding V that I'm getting because of onto-ness, because of surjectivity, the V that I will get, I mean, there will be a V, but because of injectivity, this V will be unique, which means I can, so given a W, I can get a unique V such that phi V would be equal to W. Yeah. This mapping from W to V would be called phi inverse. And we'll see that this phi inverse actually satisfies both these properties. Okay, so let me write this down properly. Since phi is onto, for every W, there exists a V in V such that phi V is equal to W, but due to phi being one-to-one, this V must be unique, right? Because two distinct V's cannot lead to the same W because it's one-to-one. So define now phi inverse W to be equal to this V, the unique V in capital V such that phi V is equal to W. Yeah, now let us check the composition. Phi inverse phi acting on a V. This is some phi inverse W. Phi inverse W has been defined to be V. This is V. So that means, and this is true for all V, in V. So this means phi inverse composed with phi is nothing but identity on this vector space V. So I start with any arbitrary V, apply phi first, I go to W, then I come back to the same V because there's a unique V, no? So there's a one-to-one correspondence between every element in V and every element in W. One-to-one correspondence. One guy is matched with another guy, another guy, and this is true for, so I can pair up all of them, right? And there's a unique way of doing this pairing. Okay, so this is identity on V. On the other hand, similarly, if I have phi inverse W for an arbitrary W, this phi inverse W is defined to be V. Yeah, there's only one V, and this phi V must be equal to W, right? And this is true for all W in W, which then implies phi composed with phi inverse is identity on W. This mapping will be called its inverse. Okay, good, no? That is, whenever there is this, pictorially it means whenever there is a surjection, whenever there is a surjection, whenever there is a bijection, I'm sorry. Whenever there is a bijection, each element here can be paired up. And once this pairing is done, I can easily define the inverse map using this, using the pairing, because there's this one-to-one relationship, no? Yeah, so far so good. This is what bijection is. This bijection can be a very tricky concept, yeah? Using this idea of bijection, one can actually show some really weird stuff. For example, you'd be surprised to know that there is a bijection between R and R2. Not a linear map, not a linear bijection. Yeah, it's not a linear function, but there is a bijection. So there's a one-to-one correspondence, which means there's a one-to-one correspondence between R and R2. Yeah, listen carefully. This is so surprising, so baffling. This real line and the space. It appears to us the space is strictly bigger than the line, right? But in fact, they contain exactly same number of points because there is a bijection. Yeah, this was the idea of a great mathematician, German mathematician called Georg Cantor, uh, who proved these things. But later on, he was dealing with something called continuum hypothesis, which he thought is true. Then he thought it's not true. So he thought he had a proof. Then he had a counterexample. Then once again, he had another proof. So he went like this back and forth, and finally, I mean, played so badly with his mind that he actually went mad finally. Yeah, I can tell you the story some other time. So this is the story of bijection. So bijection means that there's this one-to-one correspondence. And in this case, in our case, when we have a linear map, which is bijective, we can immediately assign an inverse map. Now the question here is the important question, that is this phi inverse also linear? Bijection set theoretically, I have this map. So set theoretically, there is an inverse map. There is an inverse map. But the question is, but is this phi inverse also linear map? Is this also linear, provided phi is linear? So if phi is a linear bijection, so if phi is a linear bijective map, then set theoretically there is an inverse map, but the question is this also linear? Yeah, as you can guess, the answer is yes, it is also linear. Why is that so? Theorem that this is also phi inverse is indeed linear. Okay, but the question is why? How do we show this? Yeah, in fact, it will follow pretty easily. Okay, so you know what the definition of phi inverse is. Phi inverse is that particular V, phi inverse of W. So, okay, pick an arbitrary W in capital W. Phi inverse W is defined to be that V, that unique V for which phi V is equal to W. I have said sorry too many times. Let me write this down. Yeah, that's better. Let W in capital W be arbitrary. Phi inverse W is equal to the unique V in V such that phi V is equal to W. We have to show that phi inverse is linear, which is to show that phi inverse alpha W1 plus W2 is equal to alpha phi inverse W1 plus phi inverse W2 for all W1 comma W2 in capital W and for all alpha in F. That's what we need to show. Okay. Now, okay, because I have this W1 and W2, there exists a unique V1. This means there exists unique. Huh? This exclamation mark after the there exists means it's unique. There is this unique V1 and unique V2 such that phi V1 is equal to W1 and phi V2 is equal to W2. Yeah. So this implies phi of alpha V1 plus V2 is equal to alpha phi V1 plus phi V2 by linearity, which is the same as alpha W1 plus W2, which means this vector is a vector such that when phi acts on it, it produces this vector. But bijectivity means this is unique. So this means phi inverse. So this means, okay, since phi is bijective, alpha V1 plus V2 is the unique vector in V such that phi alpha V1 plus V2 is equal to alpha W1 plus W2. This implies from definition of phi inverse that phi inverse of alpha W1 plus W2 must be alpha V1 plus V2. But notice, this also means alpha phi inverse W1 plus phi inverse W2. That is what we needed to prove. Done. So phi inverse is a linear map. Okay. All right. So see, when we have phi, which is linear, and one-to-one, and also onto, then set theoretically there will be a phi inverse uniquely defined, and that phi inverse it follows is also linear. So that means this linear maps that are bijective, their inverses are also linear. Okay, so that means one doesn't have to go to, so when we have an injective an injective and surjective linear map, one doesn't have to go outside the category of linear maps to get its inverse. Its inverse will also be um, a linear map. Okay, so that way this linear maps kind of forms, invertible linear maps forms a group. Yeah. All right. All right. So such bijective linear maps, because their inverses are also linear, such things are called isomorphism. So bijective linear maps will also be called isomorphism. Are called isomorphism. Okay. Now, the question is, how do we even know whether a map is a bijection, whether it's isomorphic or not? I mean, it's an isomorphism or not. Okay. Turns out that for finite dimensional vector spaces, we can actually do something. We can devise some nice test by which we can check whether a given linear map is bijective or not. Okay, and that happens to be the following. This is pretty surprising. So we call this a theorem. Yeah, and once we are done with this theorem, we'll close this module and we'll reconvene for the third and final module. Okay, what is the theorem? The theorem says the following. Suppose phi is a linear map from V to W, where V and W are finite dimensional vector spaces over the same field over F, and assume that dimension of V is equal to dimension of W equal to, which is less than infinity, which means they are both finite dimensional and they have exactly the same dimension. Okay, in that case, phi is 1 to 1 if and only if phi is 1 to 1. Surprising, no? But in fact, not quite. And who comes to the rescue once again? How do we get this proof? Once again, through rank nullity theorem. Okay, let's see. So first we'll prove this direction. Okay, so we assume phi is 1 to 1. We have to show that phi is onto. Remember the criteria for one-to-oneness and onto-ness, injectivity and surjectivity. Injectivity, that is 1 to 1, is equivalent to kernel being 0. Surjectivity, that is onto, is equivalent to image being full. Yeah. Now, by rank nullity theorem, dimension of kernel of phi plus dimension of image of phi is equal to dimension of V, right? But I have assumed that kernel phi is 0. This is 0 plus dimension of image of phi must be equal to dimension of V. This is because kernel phi is the 0, the trivial subspace. But you see, we have assumed that dimension of V is equal to dimension of W. That was the assumption of the theorem. So that means this is equal. But now what do I have? I have image of phi, which is a subspace of W, right? Can it be a proper subspace? We have already seen, go back to, I think, 5th or 4th lecture, where we have shown that if there is a proper subspace, it's of a finite dimensional vector space, its dimension must be necessarily strictly less than the dimension of the whole space, right? So that means image phi here, because the dimensions are equal, cannot be proper, cannot be a proper subspace. So since dimension of image of phi is equal to dimension of W, which is finite, image phi must be equal to W. Otherwise, the dimension of image of phi would be strictly less than dimension of W. But this means phi is onto. And that is what we wanted to prove. Okay, now the other direction. Once again, it's equally simple. What we assume is phi is onto. We have to show that phi is 1 to 1. Once again, rank nullity theorem. Rank nullity theorem implies that, what does it say? Rank nullity theorem says that dimension of kernel of phi plus dimension of image of phi is equal to dimension of V, right? But we have assumed onto, no? So this is dimension of kernel of phi plus this is dimension of W, which is equal to dimension of V by rank nullity. But we have assumed that these two dimensions are equal, so they cancel each other, which then means dimension of kernel of phi is 0. Sorry, this is just equal, this is the number 0, yeah, equal to 0. But a 0-dimensional subspace means it's just the trivial subspace. Otherwise, there will be yeah. So this means kernel phi is equal to 0, which means phi is 1 to 1, and that is precisely what we had set out to prove. Okay, so that's how we prove this. So you see, what does this mean in terms of matrices? So when we have a matrix A in general, so we are defining this map from Fn to Fm, right? But here we are saying that the dimensions are equal, so it will be mapped from Fn to Fn, which means A must be a square matrix. So square matrix defines a map from f to the power n to f to the power n. That is when the two dimensions are equal. So it's a square matrix. So what we are saying in this theorem would amount in the case of matrices to the fact that for a square matrix, 1-to-1 implies onto, and onto implies 1-to-1. And because one implies the other, if it is 1-to-1, it's automatically onto. So 1-to-1 onto together, so it's a bijection, so it's invertible. So then this theorem says that, so as a corollary, we can write for a square matrix, it's invertible if and only if its kernel is equal to 0, which is if and only if its image is all of f to the n. Image being all of f to the n means the columns are linearly independent, yeah, which is the same thing as saying that kernel of A is 0. Yeah, so this is the test. How do you know whether a matrix is a square matrix is invertible? Its kernel must be 0. And if its kernel is non-zero, then it's not invertible. So it's an if and only if condition. Right. So that's how we close this module of of lecture 7. Before we proceed, so invertibility. So we have seen that bijectivity implies invertibility, right? So when the map is bijective, then you can invert this map. Yeah, and the inverse also happens to be a linear map. What if the map, the linear map, is say only 1-to-1 or only onto? In that case, would it be invertible in some sense? Would it be possible to construct some sort of inverse? That's what we will see. And we will see that this leads to this idea, these two notions called a left inverse and a right inverse, yeah, of a linear map. Okay, but how do we do that? That will require some further sophistication. That is what we'll learn in the third and the final module. Okay, but before we proceed to the third and final module, you will have to prove some some problems. So here is a homework problem. Let T be the linear operator on R3. That is a map from R3 to itself, which is defined like this. Find out whether T is invertible. Yeah. Then if so, find a rule for T inverse like the one which defined T. So the way T is defined, is it possible to find out a similar definition for T inverse? Then yeah, then there is this another map for which I'm asking what is the rank of this map, and I'm also asking that if C is a matrix given, describe the relations must the entries of C satisfy in order for Tx to be equal to C to be solvable for X in Ct 2 cross 2. Okay. And this is what this will come later in the third part. So do these two homework problems. Yeah. Okay. Once you're done with these homework problems, let's meet on the other side of the break and meet for the third and final module of lecture 7. Okay.